This is a memory module. It serves the CPU. The data required for CPU calculations and the results produced are temporarily stored in the memory. This is a graphics card. The most prominent part of the center of the graphics card is the GPU core chip. Surrounding the GPU core are the VRAM chips. VRAM and system memory have similar functions. The data required for GPU calculations and the results produced are temporarily stored in the VRAM. VRAM and system memory serve the same purpose. However, there are also significant differences between them. So in this video, let's explore together the differences between system memory and VRAM. In fact, in the early days, there was little difference between VRAM and system memory. Graphics card manufacturers directly used the DDR standard for system memory to produce VRAM. But as GPU technology advanced, people gradually realized that using the DDR standard directly for VRAM could no longer meet the demands of GPUs. So NVIDIA collaborated with ATI to propose the GDDR standard. The G stands for graphics. It's DDR memory specifically customized for GPUs. As for what DDR means, we'll explain that later. So what customizations does GDDR have compared to DDR? To discuss this topic, we still need to start with the differences between CPUs and GPUs. You've probably heard about the differences between CPUs and GPUs. CPUs have fewer cores, but each core is very powerful, while GPUs have many more cores, but each core is relatively weaker. This means GPUs are inherently suited for parallel tasks. Let's take a classic example. Here I have an image. The image is too dark. I want to brighten this image. If using a CPU, its processing flow will look roughly like this. First, this image is stored in memory. So the CPU starts with the first pixel, reads this pixel from memory into the CPU, then performs brightening calculations on this pixel. After the calculation is completed, the pixel's computation result is written back to the memory. Then it processes them one by one in this manner. Finally, all pixels across the entire image are brightened. Of course, the CPU I'm describing here uses the most primitive and inefficient processing method. Modern CPUs employ various optimizations, but broadly speaking, this is how it's handled. Now, for the same task, what would it look like if a GPU were to handle it? First, the image would reside in the video memory, VRAM. Before processing begins, the GPU's controller assigns tasks to each core. You process this pixel. Once assigned, at a single command, all cores simultaneously read their respective pixels from the VRAM. After retrieval, they process them concurrently. Finally, the processed results are written back to the VRAM simultaneously. Of course, this is also the most primitive GPU processing method I'm describing. But broadly, this is how it operates. By observing how CPUs and GPUs process tasks, you should be able to see that the CPU moves data in sequential batches. This GPU needs to transfer everything all at once. So, to accommodate the GPU's working method, the bandwidth requirement for VRAM is much higher than that for system memory. This is why graphics card manufacturers abandoned the DDR standard and instead developed the GDDR standard from scratch. So, how does the GDDR standard increase VRAM bandwidth? First, we need to understand what determines bandwidth. Bandwidth is calculated by multiplying the transfer rate by the bit width. So, what is the transfer rate? And what is bit width? Let's use a simple analogy. Suppose there's city A and city B. I want to transport goods between these two cities. We can build a road, so trucks can make trips back and forth to deliver goods. So, how can we increase the freight capacity between these two cities? First, you can build more roads, allowing multiple roads to operate simultaneously. This way, your freight capacity increases. The more lanes there are, the greater the freight capacity. These roads essentially represent the bit width. The bit width of memory is typically 64-bit. Some motherboards support dual-channel configurations. This allows you to achieve a 128-bit bit width. So, what's the bit width of a graphics card? The RTX 4090 has a 384-bit bit width. That's significantly higher than system memory. But is increasing bit width alone enough to meet GPU memory demands? Well, no, it's still insufficient to increase freight capacity. Besides adding more roads, what other methods are there? The answer lies in boosting the speed of each road, or what we refer to as the transfer rate in our formula. However, note this. In the real world, you can floor the gas pedal to make trucks go faster. But in computing, these trucks operate at the speed of electricity, nearly the speed of light. And in our universe, nothing should exceed light speed, right? So demanding further acceleration from these trucks is impossible. So what should we do? Hey, look. See how there are gaps between these trucks, right? Don't waste them. Fill them all in. In computers, there's a component called a crystal oscillator. The crystal oscillator, combined with some circuits, can generate square wave signals at a specific frequency. This signal is called the clock signal. For transmission circuits, the clock signal provides a reliable synchronization signal for the sender and receiver. It's a bit like the commands shouted in the military. All soldiers act in sync with the command rhythm to avoid chaos. For the most traditional transmission circuits, every time the clock signal oscillates, that is, the signal rises and then falls, the circuit performs one transmission. We also call one oscillation of the clock signal a clock cycle. However, it's important to note, the moment the circuit performs transmission isn't when the clock signal has fully risen, but rather during the process of the clock signal rising from low to high. This is the exact moment when it gets triggered. This signal transition from low to high is called the rising edge. The most traditional circuit performs one transmission at the rising edge. Thus, only one transmission occurs per clock cycle. This type of circuit is called SDR, single data rate. Now if you look at this clock signal diagram, you'll notice that within one cycle, there isn't just a rising edge, but also a falling edge, so we can perform another transmission at the falling edge. This way we achieve two transmissions per clock cycle. This type of circuit is called DDR, double data rate. That's right, the reason DDR memory is called DDR is precisely because it uses this technology that performs two data transfers per clock cycle. Therefore, when we see the so-called frequency in memory module specs, it's not the actual clock frequency. 4 gigabytes, 8 GB, 16 gigabytes isn't the true clock equivalent frequency obtained by doubling the clock frequency. As for the GDDR standard for graphics memory, this existing predecessor technology was undoubtedly adopted directly. After all, the name GDDR itself includes DDR. But soon, even this technology of transmitting twice per clock cycle could no longer meet the throughput demands of GPUs. So, in the GDDR5 standard, graphics card manufacturers copy the original clock signal 4 times, and then offset each of these 4 signals by a quarter cycle. A transmission was triggered at the rising edge of each signal, allowing 4 transmissions per clock cycle. At this point, the name GDDR5 was already somewhat inaccurate. It should have been called GQDR, quad data rate, instead. However, the standard name was never changed and remained GDDR. By continuously squeezing new trucks into the gaps of existing ones, they finally achieved, with GDDR6, what graphics card manufacturers had been striving for: the feat of transmitting data 8 times within a single clock cycle. So, does this meet the GPU's demands? Still not enough. Aside from building more roads and squeezing more trucks into the gaps, what other solutions exist? Actually, we can pack more cargo onto each truck. This is the PAM4 technology. When transmitting signals, a low voltage level represents 0, and a high level represents 1. Essentially, binary transmission. But in reality, we can design the voltage levels into 4 distinct states: high, mid-high, mid-low, and low. This allows us to increase signal capacity from 1 bit to 2 bits, doubling it outright. PAM4 was adopted in the GDDR6X standard. So GDDR6X doubled GDDR6A8X data rate, once more, reaching 16x speed, transmitting 16 binary data transfers per clock cycle. Applying PAM4 to VRAM was a very aggressive attempt. Many also felt it might be a step too far. As the saying goes, if you take too big a step, snap, you might hurt yourself. So, for the GDDR7 standard, the more conservative PAM3 technology was adopted, which uses ternary signaling for data transmission. After discussing all these VRAM technologies, it's clear that VRAM has exhausted every method to boost bandwidth. But looking at system memory, RAM, aside from using both rising and falling edges for data transfer, it seems to have done little else. The bus width remains eternally 64-bit, with each generation just bumping up the clock speed, and not by much. RAM, you need to step up your game. Don't embarrass yourself. Why not adopt PAM3 or PAM4 too? So why doesn't CPU serving RAM go all out on bandwidth like VRAM? Because it's genuinely unnecessary. Let's revisit how CPUs and GPUs operate. We just used an example of image processing. In this example, the GPU's processing speed is significantly faster than the CPU's. So why is the GPU so much faster in this scenario? That's because each pixel is essentially independent of the others. This allows all cores to process them in parallel. However, in reality, there are many scenarios. In fact, the vast majority of them, that cannot meet the requirements for parallel computing. For example, let's calculate a cumulative sum, adding from 1 to 100. In this case, 99 additions are required. Could we assign each of these 99 additions to 99 GPU cores, and have them compute in parallel? Obviously not, because each addition depends on the result of the previous one. So in this case, you can only use the CPU to calculate them one by one. Moreover, the data required for each operation is relatively small. So the CPU's demand for memory bandwidth isn't very high, and if you want to improve CPU performance, you can only make each computational step faster. So CPUs have been relentlessly pushing clock speeds. A few years ago, CPUs already reached 5 GHz, but in recent years, it seems they've hit a wall. In contrast, even the RTX 4090 at full load barely hits 3 GHz. The rumored 5090 might reach 3.5 GHz, but it still lags far behind CPUs in clock speed. Note that this doesn't mean GPU frequency is unimportant. Rather, compared to CPUs, GPUs gain far less from frequency boosts than from scaling up cores and architecture. For CPUs, if every operation requires fetching data from memory latency becomes critical. Latency refers to the time difference between when a processor initiates data access and when the data is actually retrieved. High memory latency means these delays accumulate with repeated accesses, drastically increasing total processing time. Typical memory latency ranges between 5060 to 7080 nanoseconds. Even at this level, it's still extremely slow for CPUs. That's why CPUs have been adding more L1, L2, and L3 caches in recent years. This on-chip memory integration aims to minimize memory access as much as possible. But latency isn't as critical for GPUs. GPUs have numerous cores fetching data from VRAM simultaneously, even if the latency is higher. Because it's happening in parallel, the overall processing speed isn't noticeably slowed. It's like how teachers used to say, if one student talks for a minute, you've wasted 45 minutes for 45 classmates. That's an entire class period gone. This is a classic case of misdirection. One student talking for a minute still only wastes 1 minute for 45 classmates. Even 10,000 classmates, still just 1 minute. Not even divine intervention changes that fact. Of course, when your teacher says this, just apologize and move on. After all, they're teaching discipline, not science. But it's all about human relationships and worldly wisdom. Thus, we can see that GPUs are less concerned about memory latency. Therefore, memory latency is generally above 200 nanoseconds. The methods mentioned above for increasing memory bandwidth often come at the cost of increased latency. So, these are the main differences between system memory and graphics memory. Graphics memory evolved from system memory, but has taken a completely different development path. However, have